How to represent a molecule in wedge and dash projection? Which means what?
Above the plane, ma'am. It will be
Okay.
shaded.
Okay, fine. How about the dash? How about the dash
Below the
projection?
plane, ma'am.
Below the plane. Like suppose if you consider a tetrahedral carbon wherein the carbon is separated into four different groups, so all the four groups will not be lying in the same plane. Okay, so in three-dimensional structure, we have to show a structure in wedge and dash projection. So two substituents will be within the plane, which are shown with the normal solid lines, whereas the other two substituents, you can see one is coming towards the observer, that is above the plane, and the other one is below the plane or away from the observer, which is shown in the dash projection. Okay, dash form, you can identify that that particular substituent is away from the observer. Okay, now that is the basic thing what we have learned in the wedge and dash projections. Okay. Then next come to the Fisher projection formula. You remember this Fisher projection formula? Like here you have only the horizontal and vertical lines which are used for the representation. Now can you see this first? A carbon in the center. So carbon is nothing but the point of intersection of horizontal and vertical lines will be a carbon. Okay, girls. Can you hear me, girls?
Yes, ma'am, but voice is low, ma'am. Surrounding disturbance is more, ma'am.
Oh, one second. Now, ma? Is it okay now? Can you hear me, girls? Arshay, can you hear me?
Yes, ma'am.
Ma'am.
Now, yeah. See, in the figure projection, as I told you, that you have horizontal and vertical lines representation. So that is what you can see on the screen, where the carbon is identified as a point of intersection of these two lines. Okay. So here you are not going to represent anywhere the carbon. Okay. Now, those substrates which are lying on the horizontal line, those substrates which are lying on the horizontal line will be below the plane or above the plane. This we have already discussed in yesterday's class. So there are only two options. Okay, horizontal, the substrates lying on the horizontal line, okay, will be either shown above the plane or below the plane. So which one is correct?
Above the plane.
Yeah, good. Above the plane. And how about the substrates in the vertical line?
Below the plane, ma'am.
Very good, very good. I just so just I have forwarded the video. Here you can see. So this is what we were actually discussing. Okay. So always remember horizontal substituents are above the plane. Okay. So these are the thickened ones or shaded ones. That is nothing but the wedge. If you have to talk in terms of wedge and dash projection, so this is nothing but the wedge projection or wedge substituents, and those substituents on the vertical line A and C will be denoted in the dash projection, or this would be below the plane. So this you have to remember. This is the fundamental rule or the basic rule what you have to remember while you are drawing the structures, because many times it will be asked in the exam, Fisher projection, convert into sawhorse or sawhorse to Fisher or the wedge projection. So you have interconversions among different molecular projections even. Okay. So then next what we have learned? Sawhorse projection. You remember anything about the sawhorse? Sawhorse projection. Yes?
Yes, ma'am.
So how? Okay, I'll just play the video. At least something you can remember.
Connected in YY or Y and inverted Y, ma'am.
Okay.
Substituents which are on the right side, they are represented by wedge, ma'am.
Okay, very good. I'm sharing this video. So that is the recap of yesterday's class. So here you can see there are two conformers. Like the first one is called as the eclipsed conformer because here both the Y's are superimposed one over the other. This is the first carbon, this is the second carbon. Okay. Now I'll just show you another structure. So those substrates which are inclined towards the right direction. Okay. So those substrates which are inclined towards the right direction would be represented as wedge projection. So how to push it? This is the problem that was in our last class. Now we will use green stain. 1 second. Let's see what is happening. So now we have the region always so now I am computing the so what from the row is the text. So one at the half load so 2x minus and dA can be taken as dx. Yesterday I told you to copy one structure. You remember? And you know some and you know the questions are so finding the some integration. And the notice is and you have to write x in some integration first. X in some integration right. So for x in some integration you will write as x. In the increasing values of x, can you hear me, girls? Why there is no response?
Yes, ma'am.
You need to try that structure. Yesterday I told you to try it. So this is the Sauer's projection, what we are talking. Now here you have the Y, a Y shape. So here this is the eclipsed one and the other one is staggered. So there are the two structures here on the screen. What you can see, the second one is the staggered structure and the one in the staggered structure. Like suppose if you take the second one, here in the staggered structure you have the E substituents which is inclined in the right direction. So anything which is inclined in the right direction, that would be shown as a wedge. Okay. Yeah, this is the wedge. And any substrate which is inclined towards the left direction, that will be shown as the dash projection. Okay, so right side wedge and left side dash projection. And how about the A and F? So these are two straight lines. Okay, so these are not inclined either to the right or left. So these will be remaining in the plane. So you just have to show them with the solid lines, straight lines. Okay, so we are not going to disturb the A and F substituents. So you just have to write the wedge and dash projections for the right and left inclined substituents. Okay, I think I gave you one structure to be noted, right? Okay, this one I think. Yes, did you complete this? So BR is inclined towards which direction?
Right,
Not tell me.
ma'am.
Yeah, right side. BR is inclined to right direction. So therefore,
It will be wedge.
yeah, it will be bridge. Okay. And how about the CL? CL is inclined to the left direction. Okay, so therefore that will be shown in the diagram. See, and how about H and F? H and F
As it is, ma'am.
as it is. You are not going to disturb that. Okay, fine. Okay. So now coming to the next one, that is the Newman projection. So this is the last step of molecular representation. Okay. So here, so for this, you just have to imagine like the observer. The observer has to see these two carbons as a front carbon and the back carbon. Okay, so where will be the observer standing here? You can just see here, yeah, observer. Observer will be watching this molecule from this side, okay, from this angle. If an observer is watching this molecule, so this will be the front carbon, this will be your front carbon. And how about this one? This will be your back carbon. Yes or no? So this is the first circle, front carbon. Second circle is back carbon. So here they are giving us the and you have the attached groups like this H, D and T in the Y and inverted Y, FCl and Br to the second carbon. So while you are writing, so when you are converting this sawhorse into Newman projection, okay, so always you know this is the side view what you are observing. So first you have to show the front carbon as dot. Okay, the front carbon, you have to draw the structure of this molecule. Like here you are going to convert into Newman projection. The front carbon, remember always, the front carbon has to be represented as a dot, and the orientation of the groups, okay, so they are oriented in y direction. Okay, so that has to be retained. That has to be retained. Here you can see H will be represented, which is actually going to the left direction. H, D and T, all of them will be represented as it is. So D, there won't be any change in the positions of these substituents. H, D and T. Okay. Now, how about the back carbon? How to represent the back carbon? So back carbon will be shown in the form of a circle. Okay, so that is a Y. So in nowhere you are going to represent the Y or X. Okay, it's understood. Back carbon is Y and front carbon is X. Okay, now we are going to draw a circle which is actually showing the back carbon. And how about the orientation of these groups? Again here these groups are oriented in inverted Y. So that has to be retained, and make sure that while you are drawing the substituents, those substituents must be drawn only up to the circle. Okay, so don't extend to the dot, because the back carbon is shown in the form of circle. Okay, so can you see here? Can you see here how the substituents are drawn from where they are starting? Only they are extended up to the circle only. They are not extended to the center point. So if we are extending to the center point means what does it mean? It means that the groups are attached to the first carbon. Okay, here the groups are the F, Cl and Br, or all the three groups are coming on the second carbon. So all these must be represented to the extent that only up to the circle. Don't go beyond that. Are you following, girls, what I'm saying? Can you hear me, girls?
Yes, ma'am.
Okay. Have you understood what I said? So while you are drawing the second carbon, make sure that the substituents must be extended only to the second carbon. These should not be extended till the center point. Center point is front carbon and the circle will be the back carbon. So this you have to remember, girls, while you are drawing a Newman projection. Okay, and this is what? This is staggered structure. Staggered is anti. Okay, where you have the bond angle. Okay, they are not overlapping one over the other. You have a certain bond angle, or they are actually deviated from each other, so that it is actually not resulting in any kind of the strain. So therefore this is a more stable structure, or otherwise it is also called as anti. Okay, now coming to the second structure, where you can see the observer. Observer is again standing here. This is side view. So which is the first carbon? Which is the first carbon here? X or Y?
X, ma'am.
X will be the first carbon, and you can see how to draw this. So first carbon, always remember you have to start with the dot, and then once you have drawn a dot, you have to orient the groups okay, around this center point. So this orientation remains as it is. And then coming to the Y carbon, that is the second carbon. So second carbon have to be shown as a circle. And how are the groups oriented here? Can anybody tell me? How are the groups oriented here? See, both of them are arranged in a Y type of structure. Okay, here you have Y, here also you have Y. So how to show the orientation of the groups in the Newman projection? So hydrogen is going left side. How about the fluorine? Fluorine is also getting deviated in the left direction only. Okay, so in the previous case, you can see the orientation of groups was inverted by, but now they are oriented in the same direction as your H, D, and T. So therefore, you just have to show these groups as one below the other. Okay, one below the other. Okay, that we can't do it on the paper, right? We just have to visualize them. So what we are going to do is we just have to maintain a small distance while you're drawing, such that it actually shows that there is actually overlapping of these two substances. That is, they are lying one below the other. That is what you can see in the structure here. Okay, so below the hydrogen, which group you have to draw? Hydrogen and F, both of them are oriented in the similar direction, that is the left direction. So therefore, below the hydrogen, which group you are expecting here? Below the hydrogen, which one I should draw? Come on, girls. Yes? I've just paused the video. Quickly tell me which substrate will be lying below the hydrogen. Can you hear me, girls? Yeah. Let's just see. Look at the structure and tell me why is so much of time. Below the hydrogen, do you expect a fluorine or bromine? Which one?
Fluorine.
Yeah, fluorine. Good. So below the hydrogen, fluorine. This you can make out, no more. Below hydrogen is oriented left. Even fluorine is also oriented left. Okay. Then next comes below the deuterium. Below the deuterium, which one?
Chlorine, ma'am.
Yeah, good. Very good. Chlorine. And below the tritium?
Bromine.
Below the, yeah, very good. So what kind of structure is it forming? Is it forming an eclipse or not?
Yes, ma'am.
Yes, okay, and here you have zero angle difference. Okay, so these are not separated by uh, like the angle of separation between these two substances would be 0 degrees. So therefore, here you can see that the structure would be highly unstable because of the more strain. Okay, when compared to the staggered, which is anti, where you have the angle of separation quite good amount of angle of separation you can see among the substrates. That is why this anti-structure will be more stable. So this is what we have to learn how to draw a Newman projection. Is this okay now? Can you able to draw now? Suppose if I ask you to draw any structure in wedge dash or Fisher or Newman or Sawhorse, or if I ask you to interconvert it, can you do it now? Okay. Our next topic would be relative configuration and absolute configuration. Okay. So we just have to give the configuration for a molecule. So there are two. Okay. So I'm now using a whiteboard, girls. You just have to copy this. So actually in organic compounds, I will write this heading. Can you see this, girls? Can you make out what I have written on the screen? Can you make out what I wrote on the screen?
Yes, ma'am.
Nothing is visible on the whiteboard.
Now we can see.
Okay. I'll do one thing. I'll just use a PPT otherwise. 1 second. I think in PPT there are many options. Now can you see the PPT, girls?
Yes, ma'am. Yes.
Now I'm writing. Just let me know whether you can see this or not. Can you see this?
Yes, ma'am. You can see.
What did I write? What did I write here?
Configuration.
Yeah, very good, very good. Okay. Now there are actually different ways in which you can give the or you can assign the configuration for the molecules in the organic compounds. Okay. Can you remember any type of convention by which you can represent a particular molecule in the organic chemistry? Do you remember anything? What you have learned from your 10 plus 2? Have you heard about the D glucose, L glucose, capital D, capital L? Okay, so this is one way of giving the configuration for a molecule. Okay, or it can be small d and small l. You should be very much careful with this, girls. Can you tell me what is the reason for this? So I actually wrote three different types of. I actually wrote three different types, right? Can you hear me? Okay. So yesterday's class, the information what you have got from yesterday's class, there is a kind of representation what we have assigned for the molecules with the help of polarimetric experiment. What was that? Let me see how many of you have remembered about this topic. From the polarimetric experiment, we have assigned the molecules as dash and dash. You just have to choose the option from the screen. I gave you three options.
D and
Optical
L, ma'am.
Small d, small l.
yeah. Which one? Which D and which L? Small D and small L.
Small.
Yeah, very good. So what does this small d represent? Small d represents
Text
what?
point of view.
Very good. Dextro rotated. That means the molecule is getting rotated towards dextro means
Right.
right side, and levo rotated is L. L means the molecule would be rotated towards left side. Okay. And how about the relation between the small d and L with the plus and minus sign? Plus and minus sign. Do you have any relation among these two? Do you have relation among these two? Yes or no? Say yes or no first. Then we'll see whether we can establish the relation or not. Minus. Yeah, obviously you have the relation, right? Okay, so D is dextro, so therefore for D you can write as plus sign. Okay, okay, because the you remember, this is the plane polarized light. Okay. If this gets deviated to the right side, okay, so this is the plus sign alpha. So this is a plus sign. And if it is rotated towards the left side, then that will be represented as a minus. Okay, so for D, you are going to show as plus sign, and for L, you are going to represent as minus sign. So please do remember. And another most important point is that you don't have any relation with capital D L and small d and small l. So you absolutely, there doesn't exist any relation with this type of configuration. Okay, suppose if I say a molecule is D, okay, D lactic acid, then that, okay, sorry, if I say a molecule is D, this is a D glucose. Let us suppose this is a D glucose molecule, what we are talking about. Now, this D glucose molecule can rotate the plane polarized light either towards D, that is the text rotatory, or it can be L. Okay, then that should be small d only, or if you have D glucose, it should be only small l only. So there doesn't exist. This you have to confirm it only by means of polarimeter experiment. Okay, so don't get confused. If you write D anywhere, D glucose anywhere, so in case if you have something like this, okay, D glucose and small d like this, okay, so don't think that this D and this, since you are writing capital D for this, so you have to write small d for this. No, not like that. So this you have can establish only after performing an experiment in the polarimeter instrument. Am I clear, girls? So don't get confused among this capital D, capital L with small d and small l. So small d, small l is only for the optical rotation of the compound and optical activity of the compound, and capital D-glyceraldehyde and L-glyceraldehyde. That's why this type of configuration is called as relative configuration. Am I clear here? Am I clear here?
Yes, ma'am.
So this is the relative configuration where your relative means what? Relative means what? Relative configuration also called as DL nomenclature. Okay, DL nomenclature. Relative means what? That means you have a particular standard by which you are comparing your molecule and then you are assigning the configuration for the molecule. So therefore that configuration is called as the relative configuration. So for which you are going to take the standard as glyceraldehyde. Now what is this glyceraldehyde? Any idea about the structure? Glyceraldehyde. So there are actually two glyceraldehydes. Based on these structures, you are going to give the configuration for the molecule as D or L. So I'm writing these two. So here there is a structure wherein the OH will be on the left hand side and the other groups will remain as it is CH2 and CH2OH. So the structure wherein the OH group is on the right hand side. Okay. So this is the structure 1. This is structure 2. So in which structure the OH group is on the right hand side? Structure 1 or 2?
One.
1. So therefore this would be called as D-glyceraldehyde. Okay. And remember here, while I'm writing, I have written D and plus sign and glyceraldehyde. So this is only a dash, girl. This is not sign. Sign always have to be shown in the brackets. Okay. So this is, can see the OH molecule is on the right hand side. Okay, OH molecule right hand side and hydrogen is on left hand side. So with respect to the OH, you are going to assign the configuration for the unknown molecule. Okay, so D-glyceraldehyde is with respect to the OH position. Please do remember. Okay, and one more important point: this molecule, when its optical activity is found, it was found to rotate towards the right hand side. So therefore, they are showing the plus sign here. Okay, so you don't have to confirm the relation between the capital D and sign or capital D and small d. Okay, you just don't have a relation. Just it is showing a positive sign means it is a dextrorotatory molecule. That's it. Okay. And how about this molecule, the structure 2? Structure 2 would be called as what? L. Okay, why L? L means always remember OH is on the left hand side. D means OH is on the right hand side in the glyceraldehyde structure. L means OH is on the left hand side. Okay. And here it's being given that in the brackets it is actually showing the optical rotation as negative side. That means the molecule is a levorotatory. That's it. Okay. So that can be confirmed only by polarimeter experiment. Point plus and minus sign depends only on the polarimeter instrument. Okay, only you have to perform the experiment and then you can say whether the compound is dextro or levo. Okay, so here OH is on the left hand side L-glyceraldehyde and OH right hand side D-glyceraldehyde. Please do remember these structures. So based on these structures you can assign the configuration for the molecules. Okay. So this type of convention, D and L convention, you mostly see in the case of carbohydrates, especially the sugars. Okay. Now, now suppose if any compound that can be prepared or converted, okay, to D-glyceraldehyde will always belong to D series. Okay. And similarly, a compound that can be prepared from or converted into L-glyceraldehyde will belong to L series. Now suppose I just take another PPT. Another slide. I just write here. So I'm writing the structure. Please note down this. Is it clear, guys? Are you getting the structure? Can you see on the screen? Is it D-glyceraldehyde or L-glyceraldehyde? Is it D-glyceraldehyde or L-glyceraldehyde? This one, what I wrote.
D, ma'am.
Yeah, very good. This is D-glyceraldehyde. So on oxidation, so this is subjected to the oxidation. Okay. So what does it give on oxidation? Any guess?
Acid, ma'am.
Very good. Aldehyde will be converted to carboxylic acid group. And what is the name of this compound? This is aldehyde what we have started. So this will be glyceric acid. Okay, glyceric acid. Okay. And let me know what is the configuration for this molecule. Shall I give as D or L? Should it be D or L? Please
D,
remember D. Why? Because
D,
we actually started with D-glyceraldehyde. So always remember, if you have started with D-glyceraldehyde, the resulted compound will also be belonging to D series. Okay. I just want you people to find and change what you observe in the D-glyceric acid to D-glyceraldehyde. What change you observe? Not in the structure, below. Below the name, below the structure, I wrote the name. What's the difference between the names of these two?
rotation.
Yeah, very good. Optical rotation. Here, no doubt, the derived compound, that is the glycerol compound from glyceraldehyde. Since we have started with D series, so we just end up in D series only. But there is this change in the optical rotation of the compound. Can you make out this? We have actually started with a dextro compound, but we ended up in a levo compound. Okay, so that means there is no hard and fast rule between the D and L or D and plus. We just have to remember that we just have started D series, so we end up in getting a D series compound only. Okay. Now, I'll just write the lactic acid preparation, how we just start from the diglyceraldehyde. Please make a note of this. This is diglyceraldehyde. D. This already you are familiar with that. Diglyceraldehyde. Okay. So this on oxidation. This on oxidation. What does it give on oxidation? And other reagents. So this gives what? Any guess? Oxidation means definitely you expect the carboxylic acid group. Okay. And also it is treated with PBr3, wherein you can see the OH group of CH2OH will be replaced with CH2Br. Okay. Now this is subjected to reduction. This is subjected to reduction. Zinc H plus ions. Any guess what is the structure here? On reduction, you can see converted to CH3. Okay. So, what is the name of this compound? This is your lactic acid. The final product is the lactic acid. Now, lactic acid, D or L? D or L? Yeah, why D? Because we started with the D series, so we end up in getting D lactic acid. But remember that there is change in it might be there might be a change in the molecular rotation or it might be retained acids. Okay, but here the reported thing is the lactic acid is a rotatory molecule, but still it is belonging to D series. Okay, so that you have to remember. Next. Yeah, any doubts still here? So I'm just taking some molecules in sugar series. In sugar series, I'll draw few structures. So this molecule is called as erythrose. Okay. Now is it a D or L? How will you decide? Is it a D or L? How will you know? Fast, fast, fast. There are two carbons, right? So two carbons. Like in such cases, in such molecules where you have the more than one carbon, always remember that the bottommost carbon. So that means this carbon. So you just have to check the D or L configuration with respect to the bottom carbon. So with respect to the bottom carbon, which is right or left?
Right, ma'am.
Right side. So therefore this has to be called as D erythrose or L erythrose. So you just have to write this as D erythrose, and here you can forget about the sign. Like in case if you have to write, because it's not there in your limits, that's beyond your limit. Because this you can confirm only by the polarimeter experiment. So you can just give D erythrose. Reported molecules. Therefore, I am actually writing. This is called as triose. Is it D or L? Is it D or L?
L.
Yeah, you have gone wrong. Why? Here also you have two carbons. Again, you have to check with the bottommost asymmetric center. So here in the right. Okay. So therefore, this should be a D or L molecule.
D, ma'am.
D, ma'am.
This is also D. But the name of this compound is triose. Why? Because here you can see there is difference in the arrangement of OH group. In the top carbon you have OH right side, here it is left side. So with respect to the top carbon, we are not assigning the configuration. With respect to the bottommost carbon, we are assigning the configuration. That is why there is change in the names of these compounds. Okay. Now suppose if I write a molecule like this, let me see how you can answer this. I want the configuration of this molecule along with its name. Forget about the sign because that is imported one.
L, ma'am.
Yes? Is it D or L?
L. L.
Very good. L. Name of this molecule? This is called as erythrose. Okay. Can anybody tell me how can you write L triose? L triose. I'm drawing this. Let me know how to orient the groups. L triose. Yes, L triose. How? This will be anyhow remaining CH2OH. How about the orientation of the groups? L triose. So always L means start in the bottommost carbon. OH should be left or right? OH should be left or right?
Left, ma'am.
Left.
Left, ma'am.
Yeah. And how about the first carbon?
Opposite.
Opposite. Opposite. Very good. Okay. So likewise you can check even the D-glucose, L-glucose, okay. Else, even for amino acids also, the same type of configuration you can come across. Not only for the sugar molecules, even for the amino acids. I'll just draw one structure and I'll explain in the case of amino acids. Others you can just check it out from the PPTs. I'll just send the PPTs after the class and check from the PPTs. All those structures are big structures. I can't draw on the screen. Is this an amino acid or not? Is this an amino acid or not? Yes, because you have NH2COOH. Okay. And this amino acid is called as serine, SCRINE. And its optical activity is LEO, that is leo-rotated compound. Okay. Now, should I assign L or D for this molecule? Should I assign L or D for this molecule? So how can I assign D or L? Earlier in the case of sugar molecules, with respect to OH, we used to assign D or L configuration. Okay. Now, in the case of amino acids, please do remember, with respect to NH2, okay, with respect to NH2, you have to assign either D or L. So NH2 is present on the left hand side or right hand side? NH2 is present on the left hand side or right hand
Left,
side?
ma'am.
Left. So then therefore this has to be assigned L or D.
L.
L. So this has to be assigned as L. Okay. Another interesting molecule. Yeah, I'll just see how many of you can answer for this. Here, this molecule is called as 309. Okay, so this was an amino acid. Let me see how many of you will answer for this. Is it a D or L? Is it a D molecule or L molecule? And remember here you don't have, yeah, very good. Here you don't have one asymmetric center, but here you have two asymmetric centers. In that case, the one wherein you have the bottom carbon, the orientation of the group you just have to decide. So in the case of the bottom asymmetric carbon, you can see the OH is oriented on the right hand side. So therefore you just have to assign D. So always remember when you have more than one asymmetric centers, you always have to take the configuration of the given molecule with respect to the what? With respect to the bottom carbon, not the top carbon. If you have only one carbon, if you don't have any choice, if there is only one carbon present in the molecule, then you just have to check whether the orientation of NH2 or OH, whatever it is, whether D or L, you have to decide based upon the orientation of NH2 and OH groups. Okay. Some more molecules and draw some more structures, you can copy them. What is the name of this acid? Is it tartaric acid?
Yes, ma'am.
And this is mesotartaric acid. Okay. Is it D or L? Fast. Is it D or L?
D, ma'am.
D. How it is D? How it is D? Answer T is correct, but how it is D? Because we just have to check with the bottommost asymmetric center. Okay, right side you have OH. Okay, so the same rule you can apply for remaining molecules. Now you understood movements. We'll go for the next type of configuration, that is R is configuration, or it's also called as absolute configuration. Okay, so this is based upon the groups attached to the asymmetric carbon. So you have to follow certain rules, what you call as the R and S nomenclature rules, or this was actually introduced by three people, Kahn, Gold and Prelog. So therefore after them, this is popularly known as CIP nomenclature. Okay, CIP nomenclature. This is called what? Absolute configuration. Or also called as RS system of nomenclature. Or also called as what? CIP nomenclature, because it was actually introduced by three people. Kahn, Gold, Prelog. Okay. So shall we see how you have to assign the priorities for the groups attached to the asymmetric carbon. Okay. So there are 5 rules. Can you hear me, girls?
Yes, ma'am.
Here, Remember that the molecule should be the Fisher projection only. Then only you can assign R and S configuration. Okay. Now, let's draw this and I will try to explain. Bromine. So how many groups are there attached to the asymmetric carbon or the chiral carbon? How many groups are there? How many groups are there? How many substrates are there attached to the
Four.
central carbon?
4, ma'am.
Give the priorities for these four groups attached to the central carbon. Okay, and then you have to check for the sequence of orientation of these groups. With the help of the sequence rules, you are going to check the sequence, whether the sequence is clockwise or anti-clockwise. If the sequence is clockwise, remember, if the sequence is clockwise, then you can assign R configuration for the molecule. In case if the sequence is anti-clockwise, then you have to assign what? You have to assign S. So R stands for right side, that's the rectus. Rectus means right. Okay. And S stands for what? S stands for sinistrous, that means left side orientation, anti-clockwise. So this is the anti-clockwise rotation or the left side rotation. Okay. Shall we start the rules? Rule 1. So you have to remember girls, because many a times questions will be asked based upon the RS nomenclature, like structure will be given to you. Based upon these rules, you have to assign whether the given molecule is R or S. So anywhere if you go wrong, then marks will be deducted girls. So you'll be losing marks completely. Okay, so what does this rule 1 say? Okay, so rule 1 is the order of priority is determined on the basis of the atomic numbers of the atoms which are directly linked to the carbon, that is the chiral carbon. Okay, so here the order of priority is based on the atomic numbers of the atoms. Okay, so I'll just mention these substituents I, Br, Cl and H. So if I have to give the order of priority for these substituents which are linked to the carbon, okay, what is the order I should follow here? Whose atomic number is highest among the four? Whose atomic number is highest among the four?
Iodine.
Yes, iodine. So therefore iodine will be getting the first priority. Okay. Then among the bromine and chlorine, bromine will be getting next higher priority and chlorine definitely will get higher priority over the hydrogen. So this is the order of priority what you have to follow, okay, with respect to the atomic numbers. So the rule 1 is with respect to the atomic numbers, you are going to assign the numberings for the groups attached to this one. Okay, we'll just take this above example. Okay, so the same example I'll write. But here the fluorine is not mentioned in the order of priority. I think you can guess, right? So among these four groups, hydrogen, fluorine, chlorine, bromine, which one should be given highest priority? Which one should be given highest priority? Bromine. Okay, 1 numbering. Like this you should give. Then next priority. Does the atomic number of chlorine is high or fluorine? Atomic number of chlorine is high.
Chlorine.
Chlorine. So therefore the second priority should be given to the chlorine. And third priority, will it be given to hydrogen or fluorine? Which one will be getting the third priority?
Fluorine.
Fluorine. And now how about the hydrogen? The last priority. So the order of priority of these groups would be bromine greater than chlorine, greater than fluorine, greater than hydrogen. So this is the rule 1. So this is not the end of the story. You just have to uh, even go through the remaining rules. Okay. So still more you have 4 rules. Shall we continue for some more time? Do you have any class in the afternoon session?
Yes, ma'am. Lag will be there for one time.
Okay. Shall we stop then? We'll continue with I think tomorrow will be a holiday, so tomorrow class will not be there. Again, we'll